Hello, and welcome to part 4 of the webinar series on model-based design for DO178C software development. My name is Mike Anthony. I'm an application engineer for the MathWorks. This particular section is going to focus on verification of the model. More specifically, it's going to be verification of the model against requirements. So if we refer back to our workflow slide, this is the step where we're actually ensuring that the model is correct and is satisfying each of our requirements. This is also the step that adds I think the most significant value when you're using model-based design for software development. If you recall from the introduction conversation, you may remember the ROI slide that had the 5 red bars, and I kept referring to that big red bar on the left. Well, that big red bar on the left is really enabled by this particular scenario, and it all comes from the fact that when you're doing model-based design, the Simulink model not only is the document of your design, but is an executable environment. So we can actually start to press play and do verification much earlier than we could in a traditional software development process. So what this enables is that we can actually start to look for really not just errors in our design, but errors in our requirements, missing requirements, requirements that can't be tested, missing test cases for existing requirements, so on and so forth. It's by testing at this point in the development process and finding those errors that we can save ourselves significant amounts of time and money over a traditional software development process. All right. So if we jump into the tools, we'll actually see how to do this. All right. So again, we're working with the same model that we've been working with throughout the rest of the webinar series. So this is that logic controller model for that larger system that is the camera to follow the green ball around. All right. Now in this particular section of the workflow, we're going to start actually testing the model. Right? And anytime you start to think about testing, the very first question you have to ask is, where do the test cases come from? All right? And in the DO178C process, there's really only one correct answer to that question, and that is the test cases come from the requirements. So the idea of this part of the process is that what we want to do is for every one of our textual requirements, we want to have at least one test case. All right? And what that test case is inputs and then expected outputs. And these expected outputs have to come from our engineering understanding of the requirements. Okay? It's not acceptable for the expected outputs to be what the model tells us. That's not what we're looking for here, because that's what we're going to test against. These expected outputs have to be, if we read this requirement and we put these inputs into this function, in order to satisfy the requirement, we expect that the output should be this. And so then we're going to execute these test cases against the model and see if the output of the model is the same as these expected outputs that we've defined in our requirements-based tests. Right? Now, again, we have our Simulink model, and if you watched part 2 of the webinar series, you saw how we linked this model to requirements. So what I've done here is actually have a test document. Right? And in my experience in industry, a lot of people like to write test cases in Excel. You don't have to do this in Excel. There's actually no reason why you wouldn't want to maybe define your tests in MATLAB. You could use something like just MATLAB data or the signal builder block. There's lots of different ways that you could define test cases within the MathWorks environment. But again, based on my industry experience, it seems that Excel is still probably the most popular tool for people to use to define test cases. So what I have is a document that has basically 6 requirements, and then I have an Excel spreadsheet, and I have one test case for each of those requirements. And again, what these test cases are a set of inputs, and then I read each requirement, and I say, okay, given that requirement for this set of inputs, what do I expect the output to be? Right, so these test cases are based on my textual requirements, or in DO language, these would be my high-level requirements. So these are test cases based on my high-level requirements. Right? So what we want to do now is execute these against my Simulink model. And we want to see if my Simulink model gives us the same answer as these expected outputs. Now there's a lot of different ways within MATLAB and Simulink that you can automate testing of Simulink models. And I'm not going to go through the discussion of all the different ways to do that and which one is best. The reality is that I don't particularly care, okay? But there's a couple things that you have to recognize. So in this particular case, I'm using a Simulink test harness model. And the only reason I'm using a test harness model is because if you do use Excel to define your test cases, Excel does not have the same level of understanding of things like data types that MATLAB and Simulink do. All right. So at some point, for me to bring this data into the MathWorks environment so that I can execute it against my Simulink model, I'm going to have to do some massaging of this data. So if you recall from part 3 of the webinar series, we looked at the fact that we had to explicitly define the inputs to this particular software component. The first one is an int16. The second one is a single. All right. So when we read in the data from Excel, it's just data, so MATLAB just assumes, because Excel can't tell it any differently, that it's doubles. And so somewhere along the line, we have to restructure this data and cast it as the right data type. You could do that with a MATLAB function. I've simply chosen to do that with another Simulink model. So I'm using rate transition blocks in case the test cases aren't written at the same rate that my model actually executes. And then some unit conversion blocks to just apply the right typecast to this data before I actually try to test my model. All right. And in this case, the model under test is simply a model reference inside of my test harness. All right. And this is very key because it allows me to test the model without actually having to change the model in any way in order to be able to test it. All right. So that's all I'm using my test harness model for. Again, you could just as easily write a little MATLAB script to do all the same data typecasting, so on and so forth. I've just chosen to use Excel. So that gets the data in, but then the question is, how do we actually execute it? And again, there's a lot of different ways that you can do that. And I actually don't care which way that you choose. My only recommendation is whatever you do, I recommend that you use Simulink Report Generator as your test harness, or basically your test executor. And the reason I recommend that is so that when you're done executing all of these tests, right, you automatically get a report out that says, here's the tests I ran, here's the results. Okay, and again, just like we've talked about in the previous sessions of the webinar series, anytime you can automate that document generation, that's going to save you a lot of time. And Simulink Report Generator is really nice because it actually allows reuse of some of the most common workflows that people have as far as automating batch jobs of testing. Okay, so this is the Simulink Report Generator interface. If you've never used it before, it's basically a drag and drop. It's very similar to that configuration editor that we saw with the Model Advisor in part 3 of this webinar series. So you just construct these report templates by dragging and dropping these different report elements into your report. So you can see I have a title page, I'm taking snapshots of my Simulink model, so on and so forth. Now, the meat of this report is going to be here in the results. Okay, and so all I've done in the results, so I just set up a for loop, all right, and I'm just going to iterate through my test cases. There were 6 requirements, so there's 6 test cases, all right, and then inside of here, I'm actually just calling some MATLAB files, all right, and the reason I'm doing this is because, as very often is the case with a lot of our customers, they already have MATLAB scripts written that do all of these common tasks like importing data. All right, so I already have a function that imports my data. I may already have a function that actually executes my model, right? And almost everybody already has a MATLAB function that creates all of their favorite plots that they like to look at after they do a whole bunch of testing. So the great thing about report generators, you can use all of this stuff that you've already written. You don't have to redo any of it. All I'm saying is just call these functions that you likely already have from within report generator, because that enables you to actually get the report out at the end. And so that's exactly what I'm doing here. I've just set up a loop where I'm calling my functions that I've already written that import my data, run my sim, do my plots. And then I've written a little pass-fail check down here too, just to basically say I had the expected outputs in my Excel spreadsheet. I'm going to get the actual outputs from my Simulink model. I need to compare those and make sure that they're the same within some tolerance of my choosing. Then I'm just going to hit the lightning bolt. The lightning bolt is how we actually start the execution of these test cases. Right? So this is going to go through and it's going to automate the execution of my 6 test cases. And it's going to tell me for each of those test cases, did I pass or fail? So did the output of the model match the expected output from my requirements-based test cases? All right. So you can see as we iterate through these, I'm going to also do a plot because sometimes it's easier to look at a plot to understand if the answers were the same versus looking at tabular data. All right. So when I'm done, we'll look at the report and we'll see what happened. All right, so this is the report that I get out when I'm done. All right. So you can see I just described my model, I copied my requirements, I talked about what I'm testing, and then for each test iteration I copied in tabular form. This is what was in my Excel spreadsheet. This is what I actually got out of the model. In this case, we can look and see that there's differences, or we can look at the plot and see that there's differences. Right? And because these are different outside of my chosen tolerance, you see that I'm declaring test iteration 1 as failed. All right. And so we can go through and do the same thing for each of these test cases. And then down at the bottom, I have a summary. So in my conclusion, I'm saying that basically this test failed because the following iterations failed. So test case 1, 4, and 5 all failed, right? Meaning the output of my model did not match the expected output from my requirements-based tests. So this indicates to me that something is wrong with my model, all right? Now we can use the traceability aspects that we showed in part 2 of the webinar series, all right, to actually maybe isolate what part of the model it is exactly where the error resides. All right, so we can see that tests 1, 4, and 5 failed. And so if we go back to our test document, we knew that our test document, those test cases 1, 4, and 5, well, those were based on requirements 1.1.1, 1.2.1, and 1.2.2. All right, so then we could go to our requirements document. So let me just open it up through our linking here. All right, so we know that we failed our test cases for 1.1.1, 1.2.1, and 1.2.2. So we could use this traceability and we could say, okay, well, what blocks was it in the Simulink model, right, that are related to these requirements? So you can see the first one says, oh, well, it's something having to do with while we're in the tracking state. All right. Okay, that's good to know. That kind of narrows it down. We know it's not something wrong, say, with this little feedback loop or something like that. It's something to do with the tracking state. All right. Test case 4, so that was requirement 1.2.1. So if you look at 1.2.1, there's a couple different blocks that are here. All right. So we can click and we can say, okay, well, this transition from waiting back into tracking, okay, that's related to this requirement. All of these blocks in the camera angle calculation are related to this particular requirement. All right. And again, the tracking state. So I think that actually this one finds it. So all of the blocks in the camera angle calculation are related to these test cases that failed. All right. And if we look, we can actually go back and see that indeed what's happening is when we transition into that tracking state, something is wrong with the desired angle calculation. So clearly the error resides somewhere in this camera angle calculation, right? And without going through kind of all the tricky root cause analysis and all that kind of stuff, this is actually a very, very classic issue in the aerospace industry. It's called integrator windup. All right, so what's happening here is because we've implemented this integrator using a unit delay and a feedback loop, right? What's happening is that when we hit saturation for the output, it doesn't prevent the effective state of the integrator from continuing to increase, such that when we change directions, right, we don't immediately come off of that saturation because the state has built up through the iterations. And so again, this is a very classic problem called integrator windup, and that's exactly what we're seeing here. All right. So now we have to fix it. And for this particular issue, one of the easiest ways to fix it is by, instead of building our own little integrator using the unit delay and a feedback loop, we can instead use one of the built-in integrator functions. So rather than using that unit delay and a feedback loop, you can see that here I've replaced that with a discrete time integrator, and this is a block that I grabbed out of the discrete library in Simulink right here. And if we look inside of this block, you'll see that one of the options that's available is to limit the output, and we can put the equivalent functionality from the saturation block in our previous model into here. And when we do this, this block properly handles that issue of integrator windup. So we believe that this will fix the issue. Now, the question is, does it? And so to answer that, we take these same functional tests that we just ran, and we just want to rerun those same test cases and see if now indeed we're passing. All right? So I'm going to use exactly the same model test harness. I'm going to use exactly that same report generator file, and I'm just going to execute those again. So if you remember from the last time, it was iterations 1, 4, and 5 that were the test cases that failed. So hopefully what we'll see, so we see in figure 1, that one already looked good. So hopefully when we get to test cases 4 and 5, we'll also see that they also appear to be lining up. So when all the test cases are done and we look at the resulting test report, we'll be able to scroll down and see if we go all the way down to the bottom to those conclusions. We'll be able to see that this time, indeed, the entire test passed because all of those iterations passed. So we had one test case per requirement, and now we've shown that all of those test cases are actually passing. So in a lot of cases, the assumption would be that we're done testing, right? And so this is where you get into the interesting discussion on what is the best metric of completion for testing, right? So whenever you talk about testing, as we already said, the first question is where do the test cases come from? In this case, the test cases are coming from the requirements. We've shown that we have one test case per requirement. All of those test cases are passing. So following that logic, it would make sense for us to say that we're done. We should be able to move on. We have fully tested this model. But is that necessarily the case? So I would actually contend that it's not. And this is where the idea of model coverage really comes in. In my opinion, model coverage is really your best metric of completion for testing. So in this particular instance, we've passed all of our tests, but we also now need to understand, did all those test cases access all of the functionality in our model? Because if it hasn't, then that's indicative of a potential issue. All right, so you can see that my model is covered and I had coverage enabled. So the measurement of model coverage is kind of the third feature of Simulink verification and validation. So in the previous session, we talked about the extra capability you get in the Model Advisor with Simulink verification and validation. And in part 2, we talked about the requirements management interface, which is also part of Simulink verification and validation. The third thing that Simulink verification and validation gives you is the ability to measure model coverage. So to enable this is again under the analysis pane. And you can see there's a menu item here for coverage. And if I open up the settings menu, it's in here that I can actually enable how I want to measure coverage as I'm testing a Simulink model. So you can see in this case, I'm measuring decision coverage, condition coverage, and MCDC coverage. So these would be the ones that you would care about specifically if you're working in, say, DO178C level A. So level A has specific requirements that say you have to show 100% MCDC code coverage. Now, code coverage and model coverage, although very often are the same, are not guaranteed to be the same. And we'll talk about that in one of the later sessions when we talk about code coverage. But the approach that we suggest is that you always want to make sure that you can achieve model coverage, because if you can't achieve model coverage, the chances you'll be able to achieve code coverage later are going to be very small. So what we're looking for in this particular case is, can we achieve 100% MCDC coverage of the model? You can also see from within this menu that model coverage has a bunch of other different meanings too. So, for example, lookup table data. So, unrelated to perhaps this model, but if you have a model that, say, uses a lot of lookup tables, you could enable this. And if you run a bunch of test cases, it will be able to tell you how much of the data within a lookup table you're actually accessing. This can be a good indicator of maybe whether you're carrying along too much data. If you're hitting your limits, maybe you need more of those. So there's interesting information that can be attained from that aspect of coverage too. For this particular example, again, we're sticking just with kind of decision, condition, MCDC. So this is more about kind of your logical paths, if you will. Can we access all possible logical paths in the model? So this is what I had enabled, and then of course you have choices as far as how you want to report the result. So I'm interested in the cumulative coverage that I've achieved over the 6 test cases that I ran, one for each of my requirements. I also chose to spit out a report that gives me this. And along with that report, I chose to display coverage results using model coloring. And so if we go back to our model, we can see that's what this green and red is all about. And that's what this little window here says. So as I click on different blocks in my model, this window indicates whether I was able to fully cover each of these blocks, and I was. That's why they're green. And so we can actually see that the state flow chart is red, indicating that we weren't able to achieve 100% coverage. So if we look inside of the state flow chart, which is red, what we'll see is that inside of here, the different transitions are colored again, green or red, depending on whether we were able to fully cover them. So we can see that this transition from the waiting state back to the tracking state, we were unable to cover that. And if we look at the detailed information here, it says that this transition was never true. And so if you have something in your model that isn't covered, right, there's only a couple of possible things that this could mean. So we ran our requirements-based test. We had one test case per each requirement. So if we ran those tests and this particular piece of functionality was not accessed, one thing that could mean is that this is unintended functionality in the model. In other words, it's unnecessary and we need to delete it. All right? That's not the case here, because actually if we look at our requirements, if we use our requirements linking and look at our requirements, we can actually see that this behavior is necessary. It's actually necessary because of a combination of a couple of the different requirements. So that transition is linked to requirement 1.2.1, which says that, while the ball is in the camera's field of view, the logic controller shall command the camera to rotate to keep the ball centered. So that's part of it. If the ball's in the field of view, we need to basically be in the tracking state. But this is also combined with, so if we look at the waiting state, we can see that the waiting state is also linked to requirement 1.1.2 that says if the ball is not in the field of view, the logic controller shall command the camera to hold the current camera angle. All right, and what this transition from the waiting state to the tracking state does is really address both of these requirements, 1.1.2 and 1.2.1. All right, but it's not necessarily directly either of those. It's the interaction between those. So you could consider perhaps that this represents a valid derived requirement in the model. I think that's debatable depending on how you like to think about requirements. That's not really, in my opinion, what this is representing. So another possibility, if you run requirements-based tests against the model and something is uncovered, it could mean we're missing a requirement. Right? But again, in this case, I don't think a requirement is necessarily missing. This transition exists. It's the need for it is covered by the existence of requirement 1.1.2 and 1.2.1. So I don't think a requirement is necessarily missing. I think what's actually being indicated in this particular case is the design is complete and correct. The requirements are complete and correct. What's actually missing is a test case. Right? So in this situation, we had one test case per requirement, but there's absolutely nothing that says one test case per requirement is sufficient. Right? There are often cases where you're going to need more than one test case in order to completely test a requirement. And that's what's really going on here. So if we go back and actually look at our test document again, which remember is in Excel, if we look at the test case for requirement 1.1.2, what we'll see is we've basically created a test case where the ball is in the field of view for the first 0.4 seconds, and then the ball goes out of the field of view. All right? And the expected behavior is that while the ball is in the field of view, we're rotating the camera angle to try to center the ball. But then when the ball goes out of the field of view, we hold the camera at the angle that it last was when the ball was in the field of view. I think what we need to do is actually alter this test case or add on to this test case to be able to actually take this transition back from the waiting state, which is where we are here, into the tracking state. And so what that would mean is that we would need to just append onto this particular test case some more information that represents when the ball comes back into the field of view. All right. So if I close this, I can actually open up another test document that I have where I have made that alteration to the test case. So in this test document, again, we can see if we look at the test for requirement 1.1.2 that I've added some extra data into here. And so once we're in the waiting state, I've added a couple extra data points that say take us out of the waiting state and back into the tracking state. So this should trigger that transition. And then based on this, I have to figure out by reading the requirements what I expect our desired angle command to actually be. All right, so in this situation, I think the lack of coverage was indicating that our test cases were incomplete. But again, this is really important information, right? Imagine if we had, once we had passed all of our requirements-based tests, said we're done and gone off and generated code, it wouldn't have been until we were testing the actual code, if we happened to have come up with this particular test case for some reason, that we would have found this error. Right, so this is actually a really good example of how a latent error can kind of sneak through into the product if you're not really careful and rigorous about how you're doing testing. And this is why I think model coverage is such an important metric of completion for testing. It's not just that you have to show you passed all the test cases you've written. You have to show that the test cases you've written are actually exercising every part of your model. That's how you know that your requirements are complete, your design is complete, everything is complete, consistent, correct, and testable. All right. So with this improved test case, we need to run our test cases again. So I'm still using exactly that same report generator file, so I'm just going to rerun these. And so now what we're looking at is, one, we didn't make any changes to the model, so there's absolutely no reason why any of the behavior should change. We're particularly interested in our second test case because that's the one that we altered. We appended that additional data. So we need to ensure that our second test case still passes. So if we scroll down and look at it, and you can see again, here's that extra data that we added in. And so you can see that even with that extra data appended to cover that particular transition, our model is still giving us the correct answer according to our altered requirements-based test. All right. So in the end, what we really want to see is, again, we want to see that all of our test cases have passed, and we want to see that we have 100% model coverage. Now, before we were looking at model coverage by everything being colored in the model as green, and you can see that indeed this time the state flow chart is green, the transition from the waiting state back to the tracking state is green, and we're covering it. But this model coloring isn't necessarily the best way to document the fact that we've actually achieved 100% model coverage with our requirements-based tests. And so, of course, the model coverage tool, like all the other tools that we've talked about, has the ability to automatically generate a report. And so I've included in my test document a link to this model coverage report. And so again, this is that data artifact that we really would want to keep and be able to show that says, yes, indeed, we were able to get 100% model coverage with our requirements-based test. And again, this report is really nice. It gives you summary information at the top. It breaks it up according to subsystems, and actually will go through for every block that was associated with a logical path and tell you exactly whether it was able to cover every single block in the model. So this is a really nice report to include in kind of your package of artifacts, again, to show that your design is complete, correct, consistent, testable, and is satisfying all of your requirements. All right. So that's basically the process here for verification of the model against the requirements. And again, I can't emphasize enough that really it's this metric of model coverage. If you remember back to the introduction webinar and we talked about the value of model-based design, this is really where most of that value comes from. Okay, so again, think of this example that we just went through. The fact that we were able to find that our test cases, our requirements-based test cases were incomplete. We were able to find that, change that, and verify that everything in our model, everything in our design was correct and testable. There were no missing requirements. There's no unintended functionality. The ability to get all of that information at the design phase is what makes model-based design so valuable, because we can so much easier and more cheaply correct any errors that we find at this phase, as opposed to waiting until we're all the way down with the software written and we're testing the software in a lab on the target processor, where if we find a mistake in that instance, it's very, very expensive to actually go back and fix any of those errors. All right. The other nice thing specific for DO178C is that the measurement of model coverage is actually one of the things that's included in the DO qual kit. All right. And so this is very important, because not only can we create this measurement of model coverage, but by including that as a qualifiable tool, you don't have to actually verify the fact that we say you had 100% coverage by hand. All right, and so if you think about that, if this tool wasn't qualified, that's a lot of effort, because you would have to take that model coverage report and actually manually review it against the model and review the output of that tool to show that we didn't make a mistake in how we reported coverage. So the ability to qualify the measured model coverage is very, very useful, and that's why we include that as part of the qual kit. That's it for this particular session on verification of the model against the requirements. Now, in this particular session, we concentrated just on the one verification method, that's verification by simulation. In the next session, we're going to talk about verification using formal analysis. And it's pretty interesting, because we've talked a lot about how coverage is such an important metric to make sure that our testing is complete and our design is complete and correct. And so given that example that we just saw, we should feel very confident that our model is very complete, correct, and at this point we should feel comfortable going off and generating code. If you have time and you can watch the next session, we're going to talk about verification using formal methods, and you'll actually show that even in that model that we successfully verified against our requirements and showed 100% model coverage, there still is a potential latent error. And that's something that we can uncover with formal methods that is very, very difficult to uncover using just verification with simulation. So hopefully that piques your interest, and you'll watch the next session. Otherwise, thank you very much.